All right, so to get started in Chapter 2, Section 4, we're going to start with the question. Well, how do we solve the equation x squared plus 1 is equal to 0? Well, let's just start by checking a few things. So the first thing we know is that there are three types of real numbers. And those three types are positive, and then there's negative numbers, and then lastly, the guy in the middle, which is 0. So, when talking about real numbers, there are only three types: positives, negatives, and 0. So, let's go ahead and check each of these types to see if we can find a solution. So, one thing we notice is that if I have a positive number and I multiply it by itself, that's what it means to square. So a positive times a positive is going to be what kind of number? Well, positive. We also have the possibility of a positive times a negative, or I mean a positive times a positive, or a negative times a negative. Which would be also a negative times a negative gives us a positive. And then lastly, we can actually compute this one. 0 times 0 is equal to 0. So if we check each of these, so if x is positive, we know that x squared is positive. So a positive number plus 1 is going to be what kind of number? It's also positive. So we know that that does not equal 0. So this tells us that x can't be positive. And if we do the same thing with a negative, if x is negative, once again, x squared is positive. And that puts us back in the same case. So this is the same as above. So then our final hope is 0. But we know if x equals 0, then x squared also equals 0, and 0 plus 1 equals 1, which does not equal 0. So x can't be 0. So this tells us that the equation x squared plus 1 equals 0 has no real number solutions. And the reason for that is, for every real number, when you square it, the result is always positive. In fact, there is no real number with the property that does not have that property, except for 0, and 0 times 0 is always 0. So we need to expand our number system. And that's going to be what we're going to do in this section. So we're going to introduce a new type of number that is not a real number. So the symbol that we're going to use is I. So we're going to introduce I, which is called the imaginary unit. And the number I has the property that I times I, which equals I squared, is equal to -1. So this is a new type of number that is not a real number because it has a property that no real number has. That is, that when you square it or multiply it by itself, you get a negative number. So this has some interesting implications. So there is another way that this number is often defined. So if we look at the equation, we have that I squared is equal to -1. If we take the square root of both sides, we end up with the equation, the square root of I squared is I is equal to the square root of -1. So the imaginary unit can also be defined as being the square root of -1. This will allow us to take the square root of negative numbers. All right, excuse me. So let's take a look at our first one. If we have the square root of -4, we can rewrite this as the square root of -1 times 4, and then use our product property of square roots to split this into two radicals. So it's the square root of -1 times the square root of 4. And then we know that the square root of -1 is going to be the same as I, and the square root of 4 is 2, and we're going to write that as 2 times I. So that is the very long, verbose way to do all of this. But at the end of the day, if you have a negative under the radical, what's going to happen is that you will just get an I on the outside. Okay. Let's take a look at our next one. The square root of 75. Well, we can start off with the same strategy, -1 times the square root of 75. So we're going to have the square root of -1, which is I, times the square root of 75. But then we need to simplify our radical. So we need to find the largest perfect square that divides into 75. So if we, to remind ourselves, make a square list, we have n and n squared. We have 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49. I'm going to stop here because we're plenty far. I need to find, I'll just finish it to 100, the largest perfect square that divides into 75. And if I start checking, 64 doesn't, 49 doesn't, 36 doesn't, 25 goes into 75 3 times. So this one is what is going to work. So we're going to have I times, and if we rewrite that as 25 times 3, we do know the square root of 25, and the square root of 25 is 5. So then we would end up with, we would have our I, the square root of 25 is 5, and then the 3 would still be stuck inside the radical. So at the end of the day, we would have 5 square roots of 3 times I. So that would be our solution to that problem. All right. All right, so let's talk about this. So we want to do the same thing. So we want to simplify the square root of negative 80. Well, that's going to be I times the square root of 80. And then looking at our square list, what is the largest perfect square that divides into 80? Well, instead of using a square list, we can actually do this on our graphing device. So if we go y equals on our calculator, and then we go 80 divided by, and then we go x squared. If we go second table, it's going to show us our divisors. So 1 goes in 80 times, which isn't helpful. 2 works because we get a whole number over here, and that's really our goal. We want to find the largest whole number that we can find over here in column 2. Once the outputs in the y column get less than 2, we need to stop looking. So we go here and we go back up to our first whole number, and that tells us that 4 is going to be what we get. And let's see why. So let me clip this, and I'm going to connect it to what I did in the previous step. So this actually tells us the final answer, because this tells us what our perfect square was, because we did y equals the 80 divided by x squared. So the x column, since we're taking the square root of x squared, tells us what comes out. So the final answer is going to be that 4. Let's do a different color though. This 4. And we're going to have the square root. And what's in the y column actually tells us what's going to be stuck inside the radical. 5. And then we took the I out in the very first step. But notice, if we checked this, x squared, so 4 squared is 16, what that's telling us is that 80 is 16 times 5, and then what's the square root of 16? 4. So we get 4 square roots of 5 times I, which is the same thing. So our calculator can help us figure out what that is, and we did that by putting the number we were trying to extract the radical of over x squared. The y column tells us what stays in the radical, and the x column tells us what comes out. All right, so a couple more calculator things I do need to mention at this point. So if we go back to our home screen, and if we start and go back and look at example 1, if I go the square root of negative 4, we're going to see my calculator tells me non-real answer. And you're like, well, thanks, Professor Peterson. We already knew that because we talked about it. Well, what you may not know is that it is possible to ask our calculator to change from real mode into a different mode. So to accomplish that, we're going to hit our mode button on our calculator. And we'll notice down here, my calculator is in real mode. Right next to it, it has another choice that says A plus BI, and we'll talk about what that means in a little bit. But for right now, let's go ahead and move our cursor down and put it on A plus BI and press enter. So now my calculator, instead of being in real mode, is in what's called complex mode. And if I come back to my home screen and I go the square root of -4, this time my calculator tells me, oh, well, the answer is 2i. Oh, that's what we got when we did the first one. Okay, so our calculator can work with complex numbers. With that said, if you want to find the number I, and you look on your decimal point key down here at the bottom of your calculator, the secondary function right here is I. So if you hit second and your decimal point key, it will insert the imaginary unit, and then if you go I squared, your calculator will tell you that I squared is indeed equal to -1. All right. So let's move on a little bit and have a formal definition. So, of a complex number. So a complex number has the form A plus BI, where A and B are real numbers and I is the imaginary unit. So, a little bit about the anatomy. We have A plus BI. A is called the real part. B is called the imaginary part. And I is the imaginary unit. So it's a convention when writing complex numbers, we will always write complex numbers as the real part plus the imaginary part. So basically, times I. We always put the real part first and the imaginary part second. All right, so the good news is, with one exception, I behaves just like a variable. What I mean by that is if I had the expression 3 plus 2x plus 5 minus 3x, I would just collect up my like terms if I wanted to simplify, and that would give me 8 minus x. So we would just collect like terms. What I mean by that is that complex numbers are going to behave in exactly the same way. So if we take a look here at example 2, if I needed to simplify this, I would collect my real parts and my imaginary parts. But before I can do that, since I have subtraction outside my parentheses, I would need to distribute into my parentheses. So negative 5 plus 6i minus 6 minus 9i. And then I would collect my real parts. So negative 5 take away 6 gives me negative 11. And then I would collect my imaginary parts. 6i take away 9i would give me negative 3i. So that's the great news about the imaginary unit I, is it behaves exactly like a variable and works out pretty nicely. So it's now your turn. All right, so we could just collect our like terms once again. So 3 minus 7 gives us negative 4, and negative 6i plus 4i gives us negative 2i. I think it probably takes longer to actually type it into your calculator, but if you felt so inclined, you could type this into your calculator. So parenthesis 3 minus 6, second decimal point gets us our I, plus negative 7 plus 4i, close our parentheses, we press enter, and our calculator indeed agrees with us that the solution should be negative 4 minus 2i. So if we take a look at example 3, it wants us to calculate negative 3 plus 5i quantity squared. So when we square something, that means that we need to multiply it by itself. So we're going to FOIL this thing out. We're going to distribute our negative 3 into our parentheses. So negative 3 times negative 3 is positive 9. Negative 3 times positive 5i is negative 15i. And we keep distributing. So now we distribute our negative 5i in, or our positive 5i into the negative 3. So 5i times negative 3 is negative 15i. And then lastly, 5i times 5i gives us positive 25i squared. So now we need to collect our like terms and simplify. So we have 9 minus 30i, because negative 15i, negative 15i. And then this is where our one exception is. So recall that I squared is the same as negative 1. So we're going to get plus 25 times negative 1. So in other words, we get 9 minus 30i minus 25. And 9 take away 25 is going to be negative 16. Take away 30i. So we could also double check that on our calculator. We go negative 3 plus 5i, and we square it. And we get negative 16 minus 30i, which is indeed the same thing we got when we worked it out by hand. Our calculator agrees with our arithmetic. So when I mentioned earlier that I behaves just like a variable with one exception, the one exception we have to remember is anytime we get an I squared, we need to replace it with what it's equal to, which is negative 1. So, all right. So I want everyone to go ahead and you try number 2, but I want you to put it into your calculator if you have it. If not, work it out by hand. Well, let's go ahead and do that. All right, so to resolve that on our calculator, we just type it in. So 1 minus 2i times 2 plus 4i. We hit enter, and we get 10. Well, that's interesting. So we multiplied a complex number by a complex number, and we ended up with the number 10, which is just a pure real number. In any of our previous in none of our previous examples did we have something like that happen. So this leads us into our next definition that we want to talk about, which is the conjugate of a complex number. The conjugate of a plus bi is a minus bi. That is, the sign of the imaginary part changes. So a couple of examples. If I had 2 minus 4i, its conjugate would be 2 plus 4i. If I had negative 3 plus 10i, its conjugate would be negative 3 minus 10i. And if I had just the number I, its conjugate would be negative I. And if I had 14, its conjugate would be 14. So notice, in our definition, it says only the sign of the imaginary part changes. So the real part will be the same always. In the third line, we had just I, the imaginary unit, so we changed its sign. It was positive to negative. And in the last one, we had just the number 14. Well, the conjugate of the number positive 14 is positive 14 because it does not have an imaginary part. So when we change the sign on the imaginary part, nothing happens. Conjugates have a very interesting property. So the product of a complex number and its conjugate is always a pure real number. So if we check that, we can actually prove this. So if we have a plus bi, its conjugate is a minus bi. If we FOIL this out by distributing the a into our parentheses, a times a gives us a squared. A times negative bi gives us negative abi. And if we distribute the bi into our parentheses, bi times a gives us positive abi. And then bi times negative bi gives us negative b squared I squared. And something interesting happens. So these two are equal but opposite. So they add to 0. They reduce out. So then we also recall then that I squared is -1. So that's negative b squared times -1. And a negative times a negative makes it positive. So we get a squared plus b squared. So not only is the product of a complex number and its conjugate always a real number, moreover, the product is always the real part squared plus the imaginary part squared. So that's kind of an interesting thing that happens when we multiply a complex number by its conjugate. All right, and you might be wondering, well, why the heck do we need the conjugate anyway? So we need the conjugate to do complex number division. So to divide two complex numbers, we're going to build the fraction which means we're going to multiply both the numerator and denominator by the conjugate of the denominator. All right, so let's go ahead and do an example of that. So we want to simplify this, or divide 5 minus 3i by 3 minus 4i. So to divide two complex numbers, we build the fraction, or we multiply the numerator and the denominator by the conjugate of the denominator. So our denominator is 3 plus 4i, so its conjugate is going to be 3, or is 3 minus 4i, its conjugate is going to be 3 plus 4i. So then we need to multiply all of this out and simplify. So we start, 5 times 3 is 15, 5 times 4i is 20i, negative 3i times 3 is negative 9i, and negative 3i times 4i is negative 12i squared. We rinse and repeat for the denominator, but we know we don't have to multiply that out by hand. If we do, we'll get the same answer. But what do we know about the product of a complex number and its conjugate? It's always the real part squared plus the imaginary part squared. So it's going to be 3 squared plus 4 squared. If you don't believe me, you can FOIL it out and see that you get the same thing. So now we start collecting our like terms and simplifying. So in the numerator here, we have a negative 12i squared. But we know I squared is negative 1. So instead of negative 12i squared, it's negative 12 times negative 1. This is going to become a positive 12. So then we collect our like terms. 15 plus 12 is 27. 20i take away 9i is 11i over 3 squared is 9, 4 squared is 16, gives us 25. So then, to get it in the form a plus bi, we do termwise division, so we get 27 over 25 plus 11 over 25i. So our real part is 27 over 25, and our imaginary part is 11 over 25. So now let's talk a bit about our graphing calculator and how we can do this. So first things first, there are a couple of different models of TI graphing calculator. So if you have one of the TI-84s that is the black and white, so like the one that you're seeing right now, we're going to have to do a couple of different things to get the answer. If you have a C or a CE, one of the color versions, your calculator will do it in a slightly different way. So I'm going to show you both methods. So the first thing, in case you're not aware of it, your calculator does have a fraction notation. So if I press alpha and y equals on my calculator, once again alpha y equals, and then choice number 1 is ND stands for numerator, I can actually put fractions into my calculator. So if I put in, like for instance, 6 over 81, then my calculator is going to simplify it down to 2 over 27. And that is a great feature. So we can go ahead and try that with our complex numbers. So I go 5 minus 3i over 3 minus 4i. Let me type that in. And I press enter. And I'm going to get this error that says data type. So this only happens if you have the black and white version of the TI calculator. If you have a TI-84C or a TI-84CE, it's just going to give you the answer right away and you're done. So if this happens, we need to type the following. So we're going to take our original problem, so we're going to do parenthesis around the numerator, 5 minus 3i, close parenthesis, and then we're going to press our divide key, 3 minus 4i, and then we are going to press the math button on our calculator, and we're going to choose the fraction option. So I'll actually type all that out, but those are our keystrokes to do so. So we go 5 minus 3i, close our parentheses, divide, open parentheses, 3 minus 4i. And then our math key is the third one down here on the left side, math, and we choose fraction, and we hit enter. And our calculator gives us the following value. Here, which matches what we came up with up here. So 27 over 25 plus 11 over 25i. So just be aware, depending on your calculator, you may have to enter this differently. You can just use the fraction notation if you have a TI-84C or a TI-84CE. If you just have a plain old TI-84 that's not in color, you're going to have to type it in this way and use our fraction conversion key. Alright, so just to verify we got the right answer, we're going to go 6 plus 13i divided by 5 plus 12i. Oh, and then I forgot to press my math and fraction. Hit enter, and it looks like I should have ended up with 186 over 169 minus 7 over 169i. Alright, so the next thing we want to start talking about are powers of I. So let's go ahead and take a look at this. So we know that anything to the 0 power is 1. I to the first power is going to be I. By definition, I squared is negative 1. Well, I cubed can be rewritten as I squared times I. Well, and I squared is negative 1 times I, so that equals negative I. I to the fourth can be rewritten as I squared times I squared, which is negative 1 times negative 1, which is 1. And we'll notice we got the same thing that we started this chart with, which is 1. So I to the fifth is the same as I to the fourth times I, but I to the fourth is 1, so this is I. And we notice it starts repeating. And if we keep doing this, I to the fourth times I squared is going to be 1 times I squared, and I squared is negative 1. We get negative 1, negative I, and then we get back to 1, I, negative 1, negative I, and then we're back to 1 again. So we notice something interesting. The powers of I repeat every 4 exponents. So we notice that it's cyclic of order 4. And we can use this to our advantage when we need to calculate powers of I. So the idea is, if I want to calculate a large power of I don't care about how many groups of 4 factors I have, because every group of 4 factors of I is going to be equal to 1. So just as an example, if I add I to the 23rd power, I can rewrite 23 by going 4 divides into 23, goes in 5 times. 20, we minus 3, or minus 20, we get 3, so we have a remainder of 3. So 23 is then the same as 5 times 4 plus 3. So then I to the 23rd power is the same as I to the 5 times 4 plus 3. And if we use our exponent law, x to the n times x to the m, if we multiply 2 things together that have the same base, we add their exponents. So this is x to the m plus n. Well, I can use that rule backwards. So then this, using it backwards with my m and my n, so if my n is going to be 3 and my m is going to be 5 times 4, I would get I to the third times I to the 5 times 4. So then we have another property of exponents that's helpful, which is if I have x raised to the a raised to the b, this is the same as x to the a times b. Well, then on this one, I could have I to the third times I to the fourth raised to the fifth, using our exponent laws. But we know I to the fourth is 1, and 1 raised to any 1 power, or multiplying by 1 doesn't change anything, so 1 times 1 times 1 times 1 times 1 is just going to be 1. So at the end of the day, this ends up being the same as I cubed, and we know I cubed is equal to negative I. So this is the reason why it works here, but in general, how we want to accomplish this is the following. So to calculate powers of I for n greater than or equal to 4, we divide n by 4 and find the remainder. R then I raised to the nth power is going to be the same as I to the r power. So when we do that division of the exponent by 4, we don't actually care about the whole part. We only care about the remainder, because the whole part is going to turn into this I to the 4th raised to some power, but I to the 4th is 1, and multiplying by 1 over and over and over again isn't going to change anything. So we get the following. So let's take a look at our example. We want to simplify I to the 127th power. So we take 4 and we divide it into 127. So 4 goes into 12 3 times. We get 0. We bring down our 7. 4 goes into 7 once. 4, we subtract, we get 3. So our remainder is 3. So our theorem above tells us that I to the 127th is the same as I to the 3rd, which is then going to be negative I. So you might be thinking, well, why don't I just type that into my calculator? So let's go ahead and give that a shot. So we go I raised to the 127th power. And we'll notice our calculator gives us something different than what we got. In fact, we know that there's only 4 possible answers that you can get when you raise I to a power, but we got some of this extra stuff. Well, the problem is, even on the C's and the CEs, TI has a memory leak in their multiplication algorithm for complex numbers. So we'll notice the correct part of the answer is there. That's this minus I part. But we've got this other bit over here, 2.3 e to the negative 12. So just to remind us, the e notation, the e to the negative 12 is scientific notation. So what that number really is negative 2.3 times 10 to the negative 12th, which means I would need to move my decimal to the left 12 spaces. So this is really negative 0. And if I move that to the left 12 places, that's going to be 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 2.3. So that's that number. This is really small. But because of the error in their multiplication algorithm, it picks up this extra junk and gives us the wrong answer. So you can use your calculator, but you have to be careful. When you get these really small bits, you have to realize that that's just numerical error that's creeped in from your calculator. Or you just divide the exponent by 4 and get the whole part and the remainder, and that's pretty simple, and then you can calculate it without needing to use your calculator. All right, so let's calculate this. Not in red though. So how many times does 4 go into 731? So we have 1, 4, that gives us 3. We bring down our 3, 33. We get 8, that's 32. Bring down our 1. 4 goes into 11 twice, gives us 8. Gives us a remainder of 3. So I to the 731 is equal to I to the third, which is still negative I. All right. So that would be how we would resolve some powers of I. Well, we are now to the grand finale. We want to talk about graphing complex numbers. So the complex number a plus bi can be visualized in the plane as the point A, B. So, for example, the complex number negative 4 plus 2i could be visualized as the point negative 4, 2. So we could then use this relationship to help us graph complex numbers. So we have the number 4 plus 2i would be the same as the point 4, 2. So in that sense, the x-axis is called the real axis, and the y-axis is called the imaginary axis. So the point 4 plus 2i would be 4 and then up 2. So that would be the point 4 plus 2i. And if I wanted to graph negative 6 minus 7i, that's going to be down in quadrant 3. So I go left 6, down 7, and that would give me the point negative 6 minus 7i. Alright, so to do our last one, 5i, to help us visualize it, we could say this is the number 0 plus 5i, so it would actually be the point 0, comma, i. That would be up here on the imaginary axis, and that would be the graph of the number 5i.